So in this particular project with SigOpt, we looked at three different types of structures. The first structure that you see here at the top is just a thin film, single index refraction thin film. The second structure that we looked at are these vertical arrays of nanowires. So essentially they're tiny, very small cylinders, and these cylinders are also made out of glass. And the third structure that we looked at are what we call nanocones. Okay, so these are actually um, cone frustrums mathematically. They're not just a point at the tip. There is some sort of top diameter. So this is just an array of nanocones, and they're placed in a square lattice. So the nanowires basically are just defined by the diameter and the height, as well as the spacing between the nanowires and the square array. The nanocones are defined by the height, the top diameter, the bottom diameter, as well as the pitch, the spacing between the nanocones. So in this particular project, we looked at a multi-objective optimization problem. So we have two objective functions that we're trying to minimize: the solar reflection at 0 degrees incidence, and the solar 65 degrees incidence. So you can see that these two objective functions capture what I've described before. We want reflection minimize across a wide variety of wavelengths and different incidence angles. So to do this, we worked with SigOpt in building Bayesian optimization to efficiently search for the Pareto optimal set of these three structures based on these two objective functions. So we reformulated this optimization problem so that we're trying to minimize reflection and discover different parts of the Pareto efficient frontier.